Good morning, everyone. Thanks for joining us for this Introduction to Git webinar. This is the first of a two-part webinar series focusing on Git software development. We'll be recording this session and we'll submit a link to the recording over the next few days. Just a quick note, our next webinar, Introduction to Stash, Atlassian's Behind the Firewall Git Repository Management System, is planned for January 8th at 11 a.m. Central. As you have questions, please feel free to provide them via the questions utility in the GoToWebinar control panel. We'll queue them up and answer them towards the end of this session. On the phone today from Percipio Consulting, we have Christopher Pepe. Christopher heads up our Atlassian practice and is the brains behind this webinar. He's been working with the Atlassian product since 2004, and I'm Shayla Sander. I head up business development for Percipio Consulting, and I'll be serving as a moderator for this webinar. We've been Atlassian experts for over 5 years now and are one of 4 platinum enterprise experts in the country. Over 95% of our projects are Atlassian related, and we have over 100 clients in the United States, ranging from small 20-person companies to Fortune 20 enterprises across many different industries. We help our clients with process-centric technology solutions that facilitate traditional business process management, IT service management based on ITIL, and software development lifecycles. We support our clients in all facets of the Atlassian product suite and build methodologies and solutions across the entire line of products. So with that, I'm going to go ahead and turn it over to Chris to take us through the webinar.
Thank you, Shayla. Let's see. All right. Great. So hopefully you can all see my screen at this point. As Shayla mentioned, this is the first of a two-part series where we're going to cover using Git. And then in our next one, we're going to talk more specifically about Atlassian Stash, which is one of the many Git repository management tools that are available to you. We're going to start off by talking a little bit about the history of version control and how distributed version control systems came to be. So we're going to look at the evolution of version control. Next, we're going to look at some of the kind of real basic things that you can do with Git as a developer, the kind of stuff that you're going to do on a day-to-day basis. And then finally, we're going to look at tagging, branching, and merging, which are the actions you're going to take after you're done developing some new feature, fixing some defect, so you can actually get that code merged back with your main line and get it shipped as a product. So let's start off with an introduction to version control, why it came to be, and where it's evolved to. So pretty quick, people started to realize that there was a need to be able to keep older versions of their source code while they still worked on newer, bigger, better things. So you always want to have a stable version you can go back to, and especially when you're releasing individual versions, you want to be able to get back to that point exactly. So the original thing that people would do is make a copy of the file, give it a different name. I can actually bet that every single one of you can think of at least one person in your organization that does this today. You see this a lot outside of software development for a lot of document management, where you will make a copy of your file and put -final or a date stamp if you're really clever about it. But you'll always see this in documents that get emailed to you. The final revision usually has something in the name that suggests that they've been copying and renaming files to keep versions, so you can go back to it and keep track of where you are. It's one of the other big challenges with that, especially today, is you email out an Excel spreadsheet to 20 people. 20 people make changes, and one person has to then merge all of those changes together. So that's the kind of challenge that software developers don't want to deal with, doing all that stuff manually, and that's really where version control systems grew out of. So RCS is an example of one of the first generations of local version control systems. Now, RCS is actually still really popular today. It's used by a lot of applications and programs. The OS X, the Mac operating system, still uses RCS, as do a lot of other applications, for keeping revisions of local files. It works really well in situations where all the files live on one server or on one system, one computer, and only one developer or one application is interacting with them. So it works simply just by storing change sets. So you author your document, you write your code, and you check that into your version control system. Then you make more copy, or you make more modifications to it and check that in. The version control system figures out the diff between what it already has and the changes that you've made, and it stores that diff as a patch. And those patches just keep stacking on top of each other. So in order to go back in time to get to a previous version, you just add or remove patches to rebuild that file to the state that it was in at a given time. Like I said, this works really well in a single developer situation, but it's very difficult to collaborate. So the next generation of version control systems used a centralized server to manage all of the files themselves. That way, multiple developers can check code out, make modifications to it, commit them back in. Subversion is an example of that. I first used Subversion about 10 years ago. It's probably got another good 10 years of popularity left in it. Atlassian has some numbers around it. I forget the actual numbers, but something like 50% of their Subversion customers today expect to still be using Subversion in 5 years. It's something like that. It's not exactly that statistic, but a lot of people that use Subversion today are very happy with it and don't really have any intentions of switching to Git in the near future. And that's just fine. It is a good system. And a lot of the weaknesses with it, we have better process today that can help kind of mitigate those problems. Some of the things that it added over the local version control system are the ability to set permissions, so people can have read-only access, they can have commit access to certain repositories or certain parts of different repositories. There are also things like commit hooks, so that we can enforce process. We can ensure that you have a bug ticket ID from our ticketing system in your commit message when you commit it into the version control system, into Subversion. Or even beyond that, not only is there a ticket ID in your commit message, but it's an open ticket, it's assigned to you, you have permission to work on it. Whatever you really want to enforce, you can use commit hooks to prevent people from committing code unless it meets all of your standards. So that was a really nice thing to have as well. Some of the kind of problems with it is, as a centralized server, you have a single point of failure. You have one authoritative source. Everybody checks code out, but they don't have a full working copy of the repository, or they don't have a full clone of it, a full mirror. They just have a copy of it. There are a number of tools that you can use to get around this, so you can make copies of it somewhere else, so that if your central server were to disappear because of some catastrophic failure, you would still have backups of it. You'd still be able to get those things back. But in general, there's going to be some downtime, and there are some sysadmin tricks you have to play in order to get it to be a good, stable system. Really, the big pain, though, is the conflicts in merging. So with Subversion, it's a merge then commit setup, which is different than what Git does, which is commit then merge. So historically, you would build up a lot of different changes, then you would try to merge all of those to trunk. There'd be tons of conflicts, and then someone would have to spend the better part of a day going through all the conflicts and resolving all of them. And it was a big pain. And like I said, there's some better process stuff we can do today to mitigate that, but that's still kind of a problem that you end up with broken builds a lot. And also, as a developer, you can end up with other people's broken code breaking your build. So those are things that those are some of the things that led to the newest incarnation of version control systems, which is distributed version control systems. We're going to be talking exclusively about Git today, but there are a number of other ones. Mercurial is another really popular one. There's a bunch of others as well. Git has kind of emerged as the most popular. It's still a pretty debated thing, so I don't really want to go into the debates too much. There are good reasons to use Git. There's good reasons to use Mercurial and the other tools as well. But we're going to focus on Git as it's kind of the most powerful of the tools. So Git was originally developed to manage the Linux kernel, which is a worldwide network of developers of varying skill levels, of varying access to different parts of the kernel. So a lot of challenges were realized using centralized version control systems. It was on Subversion for a long time. There were a number of challenges with managing how people could actually get code in there and how people could submit patches and stuff like that. So Git was devised as a way of being able to better manage that. So the main difference is that it's a distributed as opposed to a centralized version control system. So instead of checking out the code and having a working copy on your desktop that as a developer you work on, you actually mirror the entire repository. So you get a full working copy of the repository on your system. At that point, once everyone who has cloned the repository now has a full working copy of that repository, and any one of those nodes can become the new master if you want to have. Typically, people will have a single kind of authoritative repository. So if you're using a tool like Stash or GitHub, the repository that lives there is usually the authoritative canonical repository. But you can daisy chain them. You can do a number of different things with Git because they're all working repositories. And as an individual developer, you commit to your local repository, and then you push those changes, you merge them with any number of remotes. So you can have a number of different remote heads that are all masters. They can all have different purposes as well. There's a number of advanced workflows that we can start to use then that take advantage of the distributed nature of Git. One of the challenges that people find when they first switch to Git, especially from a tool like Subversion, is that the commands are a lot more complex. There's a lot more switches and options. There's just a lot more to building the commands. One of the nice things that Git does is it will suggest to you maybe this is the command that you need to run first. It'll kind of take a best guess at it. But there is a little bit more of a learning curve than, say, Mercurial, which is pretty similar to Subversion. You'd feel very comfortable switching to Mercurial from Subversion, whereas Git is a little bit bigger of a step. I'm actually really curious if any of you think that you have an idea of what the next generation of version control systems is. If you want to type it into the questions box, I'd love to hear what people are thinking. One of the things, if you look at the evolution of version control systems, is that the changing technologies, the increased networking of computers and disk space being really cheap and all of those sort of things, and just the way that we interact with each other, the way that people develop together, has just really changed because of the technologies that have been developing. So I'm kind of curious to know what people think the technologies of the futures are and how those are going to change the way that we collaborate with each other. But that aside, let's jump into some of the basic things that you're going to do with Git. This is just your day-to-day basic workflows, nothing too advanced, but the stuff that you're going to do a lot. So the first thing that you have to do is clone a repository in order to start working on it. And again, in a lot of the tools with front ends, this may be either cloning the repository directly, or you may have to fork the repository first and then make a clone of it, depending on what your permissions are and depending on what the workflow that particular team is using. Of course, you're going to need to be able to add files and make changes to the files that are there. Otherwise, you're not really adding any value to it. Once you've made those changes, you're going to commit them locally, and you can commit as much stuff locally as you want before you push, or you can commit and push every single time. But ultimately, in order to get those changes back into the canonical repository, the authoritative source that everything is going to build off of, you're going to have to push your local changes back up to that remote repository. And then we always make changes that we don't want to save. So we want to know how to forget changes we've made and reset our repository back to a particular point in time. So take a look at a few of those things. These are some of the common commands. Now, there's a lot of graphical tools that you can use for Git depending on what operating system you're using and what your development tool chain looks like. All the screenshots I put in here today are all just using the terminal, so the command line utility. This is kind of the lowest level and the most basic way to interact with Git. So these other tools will help abstract some of this stuff out for you and help you build the commands so you don't need to know all of the switches, and that'll make it a little bit easier as well. But I wanted to show you kind of the base level. So over here on the left side is a pretty typical workflow for pushing back into your remote repository. The first thing that you're going to want to do is pull from the remote repository. So anything that anyone else has committed, you'll get those changes and have them pulled in. If there are any conflicts, that'll cause your conflicts to happen locally, and you can resolve those before you commit your changes back up. The git status command is going to show you what untracked files do you have and what uncommitted changes do you have in the files. And there's also git diff, which would actually print out the diffs between those files so you can inspect what were the actual changes I made in each of these files. The next one I have listed here is an add command. So I created a new file. I want to add that into the repository. So now it's being tracked by Git, and we'll take a closer look at that in a little bit. Finally, what you have to do is actually commit your files. So you can explicitly commit your files with the file name, or you can use -A, which will commit all of the changes that are staged for commit. -M is just for message, and that's pretty common even among Subversion and the other tools as well. So whenever you commit a change set, you want to give it some sort of a change message so that other people can tell what did you do here, so that in the future you know what did I change in this particular commit. Then finally, you're going to push all of that stuff back up to the remote repository. So if it's GitHub or if it's Bitbucket or Stash or whatever it is, that remote repository is going to receive those changes. Now here in my pull and push, I didn't specify any other options, but you can. So by default, when you clone a repository, your local Git repository is going to be set up with that where you cloned from as your origin. So when you pull and push, it's just going to pull and push from that place. You can add other remotes as well. So you can pull and push to a number of different places. You can keep a number of different repositories in sync with each other. And you'll see this from time to time. I think Git itself is actually on GitHub and Bitbucket. And one of them is the more development repository. The other one just gets pushed to, so that there's another copy of it out there. So the commands, these are all the most common commands, but you don't use all these as much. But add, branch, checkout, clone, commit, diff, merge, pull and push. You use rebase and reset occasionally, but their use is a little bit, it's a little bit more special of a case. Status you use a lot as well. So again, if you're using Subversion or a tool like that, a lot of these commands should already be familiar to you. There's a little bit more to constructing them with Git, or Git kind of requires a little bit more information. But in general, the commands should feel somewhat familiar. So let's step through actually cloning a repository, adding some files, pushing those changes back up. So for this whole first section, we're going to work on master. So in Subversion, it's called trunk. In Git, it's called master, but it's just your main branch. It's the one that you automatically get when you create a repository. So here our command is git clone and then a URL. Again, all the different front end tools that are out there will construct this URL for you. All of them have a clone button. Then when you click on it, it gives you this command, and you just copy it and paste it into your terminal. If you're using some graphical tool, there'll be a different way to do it. But basically, you're going to navigate to the repository that you want to clone. And then it's actually going to clone. So it's going to take the entire repository, compress it, send it to you over the network. Then your local workstation is going to expand it and initialize and do all the things it needs to do. So you have a full working copy of that repository. So here you can see there's the actual clone command itself. The stuff gets downloaded, it gets expanded. Now you have a full working repository. Now, if your remote disappeared because of some catastrophic failure, you have the full working repository on your workstation. This could be the new master. You could clone this somewhere else. Any of the clones that are out there can be there doesn't need to be a real master, and that's the whole point of having the distributed version control system. Is you can daisy chain them off of each other and build very complex workflows and permission schemes by having multiple clones and different dependencies between them. So now that you've cloned your repository, you want to start developing. So you're going to go off and develop. You're going to have a new feature, a defect that you want to fix, something that you're going to need to do. So again, in this case, we're still just working on master. This is generally not what you want to do unless it's a single developer situation and you're just using Git as your version control system. But here, the first command is an echo, and that just creates a file. So all I did was just write that line to a file so that it had a change to look at. Running git status shows us that we're on our master branch and that we have an untracked file. So if you look down at the very bottom, you'll see that Git's suggesting to you that there are untracked files present. So using git add would allow you to start tracking those files. I keep forgetting that I have these arrows in here, so I'll get it eventually. So again, we're on our current branch. There's nothing new in there. So Git is going to suggest us what we need to do in order to start tracking that file. So of course, that's exactly what we want to do, is we want to track that file and then we want to commit it into our repository. So we use the git add command, just as Git suggested we do, to add this file to our repository. Next, we want to commit it. So here I have explicitly given the file name that I wanted to commit, as opposed to using just -a. I could have done it either way, because in this case I only have the one change. It would have done exactly the same thing. But if I modified a number of different files, and in doing so I fixed 2 or 3 different defects or added a new feature, I can explicitly commit individual files so that my commit message relates to what I changed in those files. And if you forgot what you did, you can use git diff in order to show you the diff, or the change set itself, what code changed. And then you can use that to remember what things did I change in these files. The better way around that is just commit more frequently. That way you don't have to worry about what sort of things you changed. Commits are really cheap, and we're just going to eventually push the whole thing up anyway. So you might as well commit often. In doing the commit itself, Git spits out a whole bunch of stuff. We see that the new file is created with a certain set of permissions, 644 in this case. Running git status again, it tells us we're still on our master branch and that there's nothing to commit. So all of our commits, or all of our changes, have been committed. So in doing this, all we have done is we've added a new file and we've committed it to our local repository. So at this point, our upstream, our remote, has no idea that we've made any changes. We've only made those changes locally. So finally, the thing that we want to do is push that back to our remote repository. That will kick off a build in our build system. That will allow other developers to see these changes that we've made. So the next time that they pull, they'll get these changes into their branch. Or I guess in this case, we're all working off master. The next time they merge master into their branch, they would get these changes. So here again, I just specified git push. I didn't tell it where to push to, so it's just going to use the default location, which is where I cloned from. I could have specified a different remote there as well, and I can give different push options. We'll see one of those when we get into tagging and branching. So it does the same thing. It takes the delta as opposed to the whole repository, but it compresses it all up, ships it all back to our Git repository, where it gets uncompressed and then merged together. And in this case, we're just pushing from our local master branch to our remote master branch. Here I've explicitly called out stash, but it doesn't need to be stash. It's whatever your remote repository Git management tool is. So if it's GitHub, GitHub Enterprise, Bitbucket, Stash, any of the other Git hosting websites that are out there, they're all going to work the same. So for getting changes, the whole top part of this is really just making a change to a file and showing that it's there. So the git diff that you're seeing here is just showing that just creating a file line that I'd put in there. I added 3 more lines of that same text to the file to make a change. And then I want to forget that. So to forget a single file, all I have to do is check that file back out again. So by doing git checkout and then my file name, that's going to go into my local repository, take the last checked in version of it and check that back out, and then overwrite those changes. So you see that when I do a diff and a status, that it shows no changes. So that's an easy way to forget the changes in an individual file. And then using reset, you can do the same for the whole repository. I've said it a number of times. It's hard to jump into Git. I actually switched to Mercurial first and then switched to Git because I came from Subversion. And that was an easier progression for me, but it meant that ultimately I had to migrate everything from Subversion to Mercurial and then from Mercurial to Git. There's actually a way you can maintain a Git and Mercurial repository in sync with each other, but it wasn't working that well for me, so we just cut over wholly to Git. But always remember that whatever problem you're experiencing, especially when you first switch over to Git, the initial problems that you're going to have, lots and lots of people have already had these problems. Lots of people have already solved these problems, and lots of people are talking about these problems on the internet. So take your favorite search engine and search for whatever the thing is you're looking for. You'll almost always end up on Stack Overflow and find the answer there. Kernel.org has all of the official documentation. Although when you're just looking for a quick example of how to do something, the official documentation isn't always the easiest place to look. But there's lots and lots of Git resources out there. So don't waste a lot of time trying to figure a command out. Just go look up what it is you're supposed to be doing. So let's move on to branching and tagging. So let's just talk quickly about what tags are, and then we'll move into branching strategies. And I don't think we'll touch on local versus remote branches, hopefully. So tags are just a way of remembering an individual commit. So each commit has a unique ID. That's true for every version control system that's out there. There's some way of identifying an individual commit. Tags are just an easy way of being able to identify a specific commit. So they're just a point in time. One thing to note on here, the second line is git push origin -- tags. When you create tags, they're only created locally. So if you actually want those tags to be in your remote repositories, you need to explicitly push them up to those repositories. But here we are looking at the commit log. So on the right-hand side, we're looking at our master branch, which is what we were doing all of our development on. On the left-hand side, you see the tag for version 1.0.1. And you'll notice that it ends at commit C910FD3. That was the unique identifier for that commit. And if you follow the arrow, you see that exact same commit exists on the master branch as well as at the tag. But then the master branch continues on. So we continue developing. We release that version and we continue developing. So the tag is really just a point in time. It's just a pointer back to a specific commit. That way we can remember where we were and jump back to that historical point if we need to. So that's really all that tags are. So next we're going to move on to branching and have a very good transition slide here. So I'll just talk a little bit about branching and then we'll talk about feature branching. So everything so far that we've done, we've only talked about working on master. That has a lot of obvious problems. Most notably that you could be committing broken code back in, and that's going to affect other people. That's going to break the build. It's going to do all sorts of things you don't want to do. That's really where branching came from. You can use it in Subversion and other tools as well. But with Git, branching has really been embraced and is really a main part of the workflow. So there's two different workflows that we're going to look at here, feature branching and Git flow. And feature branching is really just kind of a subset of Git flow. But it's a branching strategy that's a little bit different from how we historically did things. So historically, developers might have their own branch, or we'd have different branches for different things. But feature branching is a newer idea, which makes it it's a nice development workflow. So the yellow that you have in the middle is our master, and then our green and our blue are two different features. So we have a new feature that we're going to implement. We have a bug that we're going to fix. So we create a branch for that specific feature, or that specific bug. And then in the Atlassian world, that will actually tie back to an individual ticket within Jira as well. So you have a bug within Jira, or you have a user story that you're telling within Jira. So you create a branch specifically for that. There's actually some nice new features if you're using Stash and Jira together, where from Jira you can actually create a feature branch for a given issue. And there's some other stuff. We'll cover more of that in the Stash webinar next time. But a lot of the tools these days are facilitating these Git workflows because they've become very popular and they work really well. So for feature one, we create a branch, we go off, we do all of our development, we do all of our testing, make sure everything works, then we merge it back into master. Similarly, feature two is off and developing on its own. And with feature branching and with commit strategies and things like that, you see that things are moving towards committing more often, doing smaller chunks of work, having smaller amounts of information in flight at any given time. So when there's conflicts, when there's other problems, when other people are trying to develop their features that depend on yours, there's kind of less stuff that's just hanging out there. We're not doing these big atomic commits anymore of the entire version gets committed at once, where everything that I've worked on for the last 6 months gets committed in one shot. You'll even see that some teams have really, really embraced continuous deployment. Some teams are deploying hundreds of times a day. So when you're doing that, the change sets are very small. The conflicts are going to be very few. And the assumptions that you're making about features that other people are working on are going to be more and more accurate because you're taking smaller and smaller snapshots in time. If you're doing continuous deployment, it may not work as well to use something as advanced as Git flow. But if you're managing a product, this is the workflow that the Atlassian suite is using. So when Jira comes out with a new version, they're using this general workflow. Git flow is a superset of feature branching. You'll see the bottom two blue ones are still feature branches. There's just a number of other branches that have been added as well. So here the master branch is still our main release branch. The difference is it only ever gets merged to, and we only ever merge to it once we have the actual authoritative release that's going to go out. There's never any changes made to anything that makes it into master. There's a hotfix branch, so that if we do make a release and then something is wrong, we need to fix it, we can fix it in the hotfix branch and then push it back into master in order to get that bug fixed and get the change out into the wild. But still, master is going to always be merged to and then tagged for that version that's being released. And it's only ever merged to when we have a version 2 release. There's also the release branch, and that ends up being more of kind of a staging area. So once we think the release is all done, we can merge up to that. Only from the development branch would we merge to the release branch. And from there, we can go through all of our testing, do more QA, get human testing in there. And if we find any problems, we can fix them up before we merge to master and make an official release. And then finally, there's the development branch. That's the main working branch. That's what all of the developers are going to pull changes from or merge changes into their feature branches from. That's where they're going to merge all of their features back into as well. And then, of course, the feature branches are where the work is actually done. So as a developer, I say, I'm going to tell this user story. I make a feature branch for that user story. I go off, I tell the story, I merge it back to the development branch, and we continue on that way. And then if you're running Scrum at the end of the sprint, we're going to take our feature branch or our development branch, potentially merge that up into our release branch once we've actually completed all the features that we're going to for the next release. So finally, we should talk a little bit about merging, since I keep talking about it. It's a really big part of the branching strategy, and it's a really big part of Git. So the whole point of merging is to move your code back and forth from one to another. It allows you to keep your development branches up to date. It allows you to keep your master release and other branches, depending on what your Git workflow is. It allows you to take your development changes and push those up into those branches as well. It also moves conflict resolution to the developer side as opposed to up in the main repository side of things. That way, you can resolve conflicts before you merge. So that way, you're not breaking other people's builds. You're not breaking the main build itself, and you're not pushing broken code back up into the main repository that everybody is feeding off of. So the whole point of merging, as I said, is to move code back and forth from one branch to another branch. Down on the bottom, you see a pretty typical branch development flow where we have each of the lines, the purple, blue, and green line, represent a different branch. And then the connections between them represent merges between those branches. So you can see that branches spawn off of each other when a new branch is created from that point in time. And then branches get merged back together. A popular part of the feature branching workflow is that once you've completed that feature and you merge it back into your master or your whatever your development branch is, that you then delete that branch. So in that case, you'd actually see features come out, be created, and then be terminated when they get merged back in. So we're still going to have the problem of conflicts. That's always going to be the problem. A conflict is going to occur when a file is changed on two different branches, and then those two branches are merged together. By committing much more frequently, we'll get smaller conflicts, so they're easier to resolve. But here in this case, I created a file called conflict.txt. I modified it in both branches So then when I went to merge master with my development branch, my admin tools branch, it causes a conflict. And that's what you see printed out in the bottom of this screenshot here. So in the head of the file, there was one line. That's my local admin tools branch. And then on the master file, there was a different change. And because they were both changed from the time that I actually last pulled into my admin tools branch, my development branch, because both of those files have changed, Git doesn't know which one should be the winner. So it throws a conflict, and then we have to go manually change this. Now, when you do this, there's a handful of steps you have to go through. You have to go and fix this file. You have to recommit it. You have to re-merge. And if you don't do it in the right order, it's not going to work. But Git will also walk you through that. And again, if you just go look it up online, you can find really good explanations of what the merge conflict workflow looks like. And then finally, I wanted to talk about pull requests. Pull requests aren't really part of Git itself, although they really have kind of become a part of it. All the web front ends or all the front end tools that are out there to manage Git repositories have pull requests as a feature. It's a really useful tool. So I think it's worth talking about, even though it's not officially part of Git. If you use a tool that has a front end, you're going to have pull requests available to you, and it's a really nice workflow. So you can use pull requests to merge branches together or to merge code from multiple repositories. So before I said when you clone a repository, you have a full working copy of it. Well, if you have your permission set so that nobody except for an authorized group is allowed to commit back to your repository, you'll see this on GitHub and Bitbucket social coding websites where people have published their code and people that they don't know are contributing to it. So the Linux kernel is a good example of that. What I would do, so if I published a application and you found a bug in it, you would go and clone my repository, but you might not have permission to clone it, so you might have to fork it. So you'd make a fork of it, and now we would both have two working copies of it. You'd make your changes, push it back up to your fork, and then create a pull request. So I could pull from your repository back into my repository. The other way to do it is between branches. So from my development branch, I can create a pull request that you have to approve to get it merged into master. So before my changes can get into the product, it has to go through a pull request. One of the really big advantages for doing this is that we get a nice lightweight code review tool. So Atlassian's Fisheye, and there's a bunch of other tools out there that do it as well, give you really good in-depth code review. But you don't always need that level of code review. And if you're using Git, you have things like pull requests to do these nice lightweight code reviews. So it's still going to show you the difference between the requested code and what your actual code base is. You can go through, comment on it, have dialogue back and forth. If I made a pull request and you rejected it for some reason, or if you gave me a comment that says, hey, instead of doing it this way, why don't you do it this other way? I can go off, make those changes, commit them back to my repository. The pull request is automatically updated with those changes. We can look at all the different commits that go in them, and we can work back and forth on it until it's in a place where you think that it's acceptable. And then it can be merged into your repository or into your branch. The bottom right corner, these are screenshots out of Stash. So different tools have different rules that they'll let you build up. But these are kind of general things that usually you want. A certain number of approvers. So again, if we're managing a really large product, maybe 3 people have to approve a pull request before it actually makes it into, before the merge is allowed into the main branch. Or maybe it has to be built a certain number of times. These are all permissions that you can build up to control the flow of how code gets into development branches and release branches and things like that. So pull requests are a really valuable tool as well if you don't want developers to be able to directly merge between branches. And of course, code review is a really good thing that we all should be doing anyway. So this is a really great mechanism that's already built into the tools you're going to be using. So that was what I wanted to share with you today. It's a pretty light overview. There's obviously a lot more to Git, but it's a really big animal. We just don't have time to go into all the details. So I see that some questions are coming through, so we'll take those now, and hopefully I can answer those for you. And then we'll need a few minutes to wrap things up. So if Shayla could come back on and help me look through these questions.
Yeah, thanks, Chris. So our first question is, if there are copies everywhere, how do you handle security where you may not want everyone to have access to all the sources? Example, you may have contractors or secure pieces of the system.
That's a really great question then, and that's actually exactly why we want to use Git, is to be able to control all of that. So especially with Stash and these other tools, GitHub, Bitbucket, all of them have the advanced permissions wrapped around it, but you have explicit control over who has access to which branches, to which parts of the repository. We didn't talk about it, but Git actually allows these things called submodules as well. So you can have a number of Git repositories kind of embedded within a bigger repository, or they can all be dependent on each other. So you can use the permissions so that as a contractor, I'm only allowed to check out a certain part of the repository, and I have no permission to push back into it as well. So I can only work on the little piece that I'm working on, and then it has to go through a pull request or some other mechanism where you have to approve all the changes I made to get them back into the main repository. So the repository can have permissions at a number of different levels. Plus, like Subversion, where we have commit hooks within Git, you have the commit hooks, and those operate locally. There's also pre and post receive hooks as well. So there's a number of different things that you can do to control who's allowed to commit back to your repository, what mechanisms they have to commit back into it, and then once those merges, I guess they're not really commits, they're really merges, because you commit locally and then you push to merge that code to the remote repository. But once those merges occur, then you can use that to notify external systems like your build system. That was a little bit of a divergence, but the main answer is that while there can be copies everywhere, you can control exactly what people are allowed to copy. So they can only get access to the things that you want them to have access to.
Okay, great, thanks. Our next question is, in Subversion, when you reintegrate a branch, the commit messages are not reintegrated into the main branch, causing a loss of information unless you look at the branches. How does this work in Git?
I'm sorry, can you repeat that?
Sure. So in Subversion, when you reintegrate a branch, the commit messages are not reintegrated into the main branch, which causes a loss of information unless you look at the branches. How does this
Okay.
work in Git?
All right, I understand. So I'm going to give you an answer, and hopefully I'm not wrong. I could be wrong about this, but I don't believe that's the case with Git. I think that all of the commit messages come through. I would have to run off and check something to validate that's actually true, but just thinking through the merging that we've done, I don't believe that our commit messages were lost, because when you're committing locally, even on the branch, is that true? Yeah, I think it is the case that Git brings all of those commits from the branch over, but I could be wrong about that. I'm gonna pause my screen and go look. So let's go on to the next question, Shayla, and I'm gonna try to validate that real quick.
Okay, and then we just had Tim chime in and say that in Tortoise Git you can contain commits from different branches. So I don't know if that helps.
Okay. Yeah, I'm pretty sure that's the case.
Okay, great. Next question. Is there a difference in performance between SVN and Git?
There is a difference in performance. Git is more efficient in some ways. Let's see. It just comes down to some operations are more expensive and others are cheaper, but in general, Git is going to be more efficient. But to go into the specifics, I'd have to go refresh my memory on some of those things.
Yeah, and to that end, some of the studies that Atlassian recently released, they found that Git is actually 325 times faster than SVN.
So there may be some situations like temporary file storage or temporary usage, because Git does a lot of things. When you clone, it will peg the CPU and use a lot of memory because it's compressing all of those files. But it's all really well-known stuff, and it actually scales very, very well. Atlassian has a study they published on that as well. So there's formulas you can use to gauge how many system resources Git is going to take based on your development environment.
Okay, thanks.
Yep.
I think that's the last question. Does anybody else have any other questions?
Yeah, so looking through my commit history here, all the commits that I made on a branch are included when I merged. So I don't believe that you'll lose that information anymore.
Great. So it looks like that's the end of the questions. Thank you everybody for attending. Again, our next webinar is going to be January 8th at 11 a.m. and it's going to be an introduction to Stash. Thanks and have a great evening.